Let's begin. Welcome to the last session of Asiacrypt conference. So the last session topic will be on quantum random oracle, part 2. And the first talk will be online, given by Jin Rong. The scene is yours.
Can you hear my voice and see my slides?
Yeah, we can see the slides.
Hello everyone. I'm Jinrong Chen from National University of Defense Technology. Today, I will present our work on tighter proofs for the PKE to KEM transformation in the quantum random oracle model. My presentation can be divided into three main parts: background, reduction for KEM, and our proposed reprogram after major technique. PKE and KEM are fundamental cryptographic primitives. PKE is used for data encryption, while KEM is used for key management. PKE consists of three algorithms. The key generation algorithm outputs a public key PK and a private key SK. The encryption algorithm uses the public key to encrypt the plaintext M to obtain the ciphertext C, and the decryption algorithm uses the private key to decrypt C to obtain the plaintext M prime. The correctness of PKE requires that M prime should be equal to M. KEM consists of three algorithms too. The key generation algorithm generates a public-private key pair. The encapsulation algorithm uses the public key to generate a key K and ciphertext C, and the decapsulation algorithm uses the private key to recover K prime from C. The correctness of KEM requires that K prime should be equal to K. Improvable security. The security of a scheme is typically modeled through a game played between a challenger and an adversary. For PKE, the security notion of OWCPA is defined by the adversary's ability to guess the plaintext corresponding to a randomly encrypted ciphertext. For KEM, the security notion of INDCCA is defined by the adversary's ability to distinguish between a random key and the key related to the ciphertext C star. In addition, the adversary can query a decapsulation oracle on any ciphertext different from C star. When the adversary is restricted to making at most a single decapsulation oracle query, the security notion becomes IND1CCA. Additionally, in the random oracle model, we introduce random oracles to simulate the hash functions used in the scheme. Note that the hash functions used in practice are public. So, an adversary with quantum capabilities could run these hash functions on superposition states. Therefore, when considering post-quantum security, we need to prove the security of the scheme in the quantum random oracle model, which involves using quantum random oracles to respond to adversary queries on superposition states. Notably, many post-quantum KEMs in the NIST PQC standardization process are constructed from CPA-secure PKEs via Fujisaki-Okamoto transformation to achieve CCA security. This is a variant of the FO transformation with explicit rejection. In the resulting encapsulation oracle, the FO transformation uses the hash of the message M as the random value for the underlying PKE's encryption algorithm. This process is often referred to as a de-randomization. As a result, the decapsulation algorithm requires re-encryption to verify if the decrypted message M prime meets the expected condition. It is important to note that when the underlying post-quantum PKE encryption algorithm is slow, the re-encryption in this scheme can be time-consuming and susceptible to side-channel attacks. Therefore, at Eurocrypt 22, Huguenin Jumitan and Watney studied the PKE to KEM transformation without re-encryption. They used the key generation algorithm from the underlying PKE to generate the key pair and encrypt a randomly selected message M to obtain ciphertext C. The hash of M and C is then used as the key. The decapsulation algorithm directly decrypts the ciphertext C using the private key. If decryption is successful, the recovered key is the hash of M prime and C. Otherwise, the decapsulation fails. They called this method the TH transformation and proved that if the underlying PKE is OWCPA secure, then the resulting KMH is IND1CC secure. While IND1CC security is weaker than IND-CC security, it is still useful in protocols like PQ-TLS and CAM-TLS. Moreover, the TH transformation does not require re-encryption like FO transformation. They proved the security of this transformation in Rome with a loss factor of OQ cubed, and left the Q-Rome proof as an open problem. At Asiacrypt 23, Hao Dongjiang et al. Proposed a variant of the TH transformation called TRH to improve the reduction loss. The key difference is that in the decapsulation algorithm, TRH uses H star C as the return value when decryption fails, whereas star is a public value. They proved that CAMH's IND1CC security can be tightly reduced to CAMRH's IND1CC security, meaning that proving the security of CAMRH suffices to prove the security of CAMH. Jiang et al. Proved that the TRH transformation is secure with loss factor of OQ squared and OQ to the first power in Rome and Q-Rome respectively. They also showed that when the underlying PKE prime is deterministic, the loss factors could be further reduced to OQ and OQ squared. Moreover, they proved that the OQ Rome loss and the OQ squared Rome loss are unavoidable in general. But is there a special case in which these losses can be further improved? We find that, yes, when the underlying PKE prime is rigid deterministic, the loss factors are only O1 in both Rome and Q-Rome. Rigid deterministic PKEs are used to construct post-quantum KEMs, such as Enchu and classic Michaelis. Our result means that when using these rigid deterministic PKEs to construct IND1CC secure KEMs, the security parameters can be reduced further. Now, let's take a closer look at what rigid determinism means. Determinism, as we know, implies that there is only a ciphertext can be encrypted by a plain text. Rigidity implies that for each correctly directed ciphertext, re-encryption must yield the same ciphertext. This implies that the encryption map ENC-PK is bijective, assuming PKE prime is perfectly correct. Let's dive deeper into how this property reduces the loss factors in ROM and QROM. The analysis here assumes that PKE prime is perfectly correct. We focus on the simulation of the decapsulation oracle, which is crucial for the reduction loss. Let's first look at Jiang et al.'s security proof. In ROM, the challenger uses a random oracle to simulate the hash function and interacts with the adversary while maintaining a hash table list edge. When the adversary queries the decapsulation oracle, the challenger selects a random number between 1 and QH plus 1 and checks if MICI exists in list edge. If it does, the challenger returns HMICI. Otherwise, the challenger returns a random value R and records IR. Once the adversary makes the ICE query MICI to the random oracle, the challenger returns R. The probability of success in simulating the decapsulation oracle is 1 over QH plus 1. Now, when the underlying PKE prime is rigid deterministic, everything becomes much simpler. In our ROM proof, we first guess whether the decryption of ciphertext C prime will fail. If the challenger guesses that decryption fails, it directly returns H star C prime. Otherwise, it checks if there exists a pair M prime C prime in list edge, such that the encryption of M prime is equal to C prime. If it does, the challenger returns HM prime C prime. Otherwise, it returns a random value R and records C prime and R. If a later query to the random oracle satisfies the condition for M C prime, it returns R. The success probability of simulating the decapsulation oracle is now only 1/2, which is a significant improvement. In QROM, however, due to the quantum no-cloning theorem, we cannot directly record the adversary's random oracle queries. So how do we prove security in QROM? In Jiang et al.'s work, they introduced the one way to hiding O2H lemma and the single classical query measure and reprogram lemma to handle the random oracle reprogramming in the QROM. However, the use of these lemmas inherently introduces a loss factor related to Q. In our work, we address this problem by proposing a reprogram after measure technique, which allows the challenger to simulate the decapsulation oracle without the private key, while only introducing an O1 loss factor. By applying our IM lemma, the QROM proof becomes significantly simpler. After challenger guesses whether the decryption of adversary's ciphertext C prime will fail, it can directly simulate the decapsulation oracle without the private key, simply by using our IM lemma. This entire process only introduces an O1 loss factor. As a result, we obtain tight reductions, proving that if the underlying PKE prime is rigid deterministic, the loss factors are only O1 in both ROM and QROM. Now, let me briefly explain the key idea behind our IM lemma. In essence, the IM lemma in QROM simulates the decapsulation oracle in a manner similar to the ROM proof. The process consists of 3 main steps. First, we use the compressed oracle proposed by Zandri in 2019 to simulate the quantum random oracle. Instead of using a random functions to simulate the quantum random oracle, we use a compressed oracle to simulate it. We also initialize an empty data register D. When a random oracle query is made, the challenger performs a decompression procedure on the database register. After answering the query, the challenger recompresses the register. This makes D can be seen as the log of queries. Zandri proved that simulating a random oracle with a compressed oracle is indistinguishable for the adversary. In the second step, we simulate the decapsulation oracle using a quantum circuit as shown in the figure. The main idea is to measure the database register to check if any MC pair satisfying the conditions exist in the database. If such a pair is found, the corresponding value is returned. If no pairs exist, a random value is returned. And the queried ciphertext C and the random value are recorded. This step introduces a loss factors of 2. In the final step, we modify the compressed oracle as shown in the figure. Essentially, we check whether the adversary's random oracle query MC satisfies the queried condition on superposition states. For the satisfied MC pair, we returned the previously recorded random number. Otherwise, we use the original compressed oracle to respond. We prove that this modification is perfectly indistinguishable for the adversary. In conclusion, we have proved that when the underlying PKE is rigid deterministic, the PKE to KEM transformation can be tightly reduced in both ROM and QROM with loss factors of only 0.1. This is the end of my presentation. For more information and questions, we can contact with this email. That's all. Thank you.
Thank you, Shinrong, for your great talk. Any questions from the audience? Okay, if not, I have a question. So can you explain a bit more like in your new measure and reprogram? So if I understand correctly, you are able to use it in such a way that you don't get any loss away. But don't you always need to like guess which queries to reprogram? So can you explain a bit where does this O of 1 loss comes from in your new reprogramming technique?
Do you mean the difference between our work and the measure and reprogram technique?
Yeah, exactly. Yeah.
Although the names of these two techniques are similar, the underlying technical principles are quite different. The measure and the reprogram technique is more general. It randomly measures one of the input registers from several random oracle queries made by the adversary to mark the point for reprogramming. In construct, our approach is essentially a migration from ROM proof to QROM proof without involving any random measurement process. As the results show, the measure and the reprogram technique introduces a loss factor related to Q, while our reprogram after measure technique only introduces a loss factor of 1. Does this answer your question?
Yeah, that's great. Thank you.
Thank you.
Yeah. Other questions from the audience? If not, I have like two small quick questions. So on one hand, can you actually explain a bit like the motivation behind like this rigid deterministic definition, like how useful this definition is in general? Because if I understood correctly, your reduction only works for this special type of encryption that
Uh,
has.
do you mean the technical details of our post IM lemma?
No, I just meant like the motivation of this definition that you are using. So your measure and reprogram only works if your encryption satisfies this rigid deterministic property. And I was just curious if you can motivate a bit, or if you can tell us a bit more about this definition.
Why is there a loss factor of true only of true introduced in our IM lemma in step 2?
Sorry, actually, I couldn't hear you very well. Can you please repeat?
Is there why this is only a loss factor of true introduced in our step 2?
Yes, yes.
I think this primarily involves some principles of quantum computing. Simply put, in a security game, we require the adversary to output a value. The probability of the adversary outputting this value can be viewed as the L2 norm as a vector, that is, the length of the vector. In step 2, we measure the intermediate quantum state and considering two cases, which is akin to splitting a vector into two parts of analysis. When considering the final probability, we must account for the L2 norms of these two vectors simultaneously. In the process of calculating the probabilities before and after modification, we introduce a factor of 2. In other words, this loss factor of 2 is derived from the principles of quantum computing. I hope my explanation is clear and satisfies your query.
Okay, thank you a lot. And if there are no other questions, let's thank Jirong again for the great talk.
Thank you.
And now hopefully we are ready for the second talk, which is also, and the very last talk of the conference, that is also going to be online by Zhang Xia.
Can you hear me?
Yeah, can you hear us
Okay.
also?
Okay, wait.
Yeah, can you please share your slides?
Okay, can you see my screen?
Yes, yeah,
Okay.
the scene is yours.
Okay, thanks for the introduction. Good afternoon, everyone. My name is Keita Xagawa, and I'm going to present you our work on measure 1 extract, title proofs of to hiding and CC security in the quantum random oracle model. This is a joint work with He Mingliao and Rui Xue. Okay, here is an overview of this talk. I will first talk about the background and the motivation of our work. Then I will introduce our main results and the outline of the technicals. Finally, I will give a summary. Now we talk about the background. In 2017, Hop et al. Proposed some CAM variants of the Fujisaki-Okamoto transformation. These variants are also called the F-lag transformations, and they are used to transform a one-way CP secure or in CP secure PKE scheme into an ECC secure CAM scheme in the random oracle model. In the CAM submission to the NIST post-quantum cryptography standardization, the F-lag transformations are frequently used to ensure the ECC security in the random oracle model, including the final winner keybar, which uses FO cancel bot. In the random oracle model, a hard function is idealized as a random function that all parties have a set to. However, in the post-quantum setting, a quantum computer can compute hash function H on an arbitrary superposition of inputs. So to model that, the random oracle model should be lifted to the quantum random oracle model, and the QROM for short. In this model, a quantum adversary has quantum access to the random oracle. So if we focus on the post-quantum security of the FO-like transformations, we should prove their in CC security in the QROM. In fact, there have been a sequence of works have already studied this problem and provided different security proofs with different security bounds. We note that their security proofs have one thing in common. They all directly use or slightly modify the original one to hiding lemma proposed by Anru in 2014. Roughly speaking, the one to hiding lemma considers the following distinguishing problem. Here, adversary A has input Z and quantum oracle set to O, where O can be function G or H. The two functions only differ on M star. That is, for OX is not equal to M star, GX equals HX. A finally output a single bit B to guess whether O equals G or H. The Y2 hiding lemma shows that the distinguished advantage of A can be upper bounded by the success probability of a one-way adversary B, which has input Z and a quantum oracle access to G to guess the point M star. So we can find that this lemma has actually gives a reduction from a one-way style search problem to a hiding style distinguishing problem. So this is why we call this lemma one-way to hiding. One thing we would like to stress is that the Y2 hiding lemma proposed by Anru has a loss of query times Q and a square root advantage loss of B. So there are many variants of the original Y2 hiding lemma. These variants gives more power to the one-way adversary B to prove a tighter Y2 hiding bound. The purpose of pursuing a tighter Y2 hiding bound is that generally a tighter Y2 hiding bound implies tighter in CC bound of the FO-like transformation in the QROM. And this tighter in CC bound can provide a stronger post-quantum security guarantee. So in this table, we present three representative Y2 hiding variants. The CY2 hiding lemma proposed by Ambanis et al. Allows B to additionally query one star. And with the help of this oracle, this lemma reduces the loss of query times from Q to the square root of Q. Here, 1m star is an indicator function that's 1m star x equals 1 if x equals m star and 0 otherwise. The DS1 hiding lemma proposed by Bieder et al. Allows B to query both G and H, and this lemma completely avoids the loss of query times. Here, we would like to stress that having oracle access to both G and H is a stronger requirement than having both oracle access to G and 1m star, because we can compute 1m star by querying G and H, since G and H only differ on m star. For example, if we want to compute 1m star x, we can query G and H respectively to get Gx and Hx. Then we know 1m star x equals 0 if and only if Gx equals Hx. So although this lemma can completely avoid the loss of query times, it requires a stronger oracle access. Then under the same oracle access, the MRM1 hiding lemma proposed by Kuchta et al. Gives the trade-off between the loss of query times and the loss of B's advantage. This lemma has a loss of query times Q, but avoids the square root advantage loss. So when the query times is relatively small, this lemma has a tighter Y2 hiding bound than this lemma. So we have a very natural question: can this upper bound get any tighter, or can we do better than the MRM1 hiding lemma under the same requirement? Okay, so let me move on to presenting our results. First, we give a new one-way-to hiding variant named measure rewind extract or MRE. This lemma has the same requirements as the MRM one-way-to hiding lemma, but reduces the loss of query times from Q to the square root of Q. In our paper, we actually require B has oracle access to G, H, and 1M star, but it is okay to only write G and H here, because as mentioned before, we can compute 1M star by querying G and H. Then we give tighter in CC proofs of the FO-like transformations in the Q-ROM. For example, compared with the FO cancel bots, we avoid the eta-injective assumption and reduce the loss of Q squared to Q 1.5 by using our new one-way-to hiding lemma. If the underlying PKE scheme satisfies the special URR property, we can further reduce the Q 1.5 to Q 0.5, and we only require the underlying security to be one-way CPA. Here, URR property assumes that there exists an efficient algorithm REC such that REC PK MC equals R, where C is the encryption of the plaintext M under the randomness R. Actually, our proof is also worked even we consider a stronger in QCC security, where the adversary can make a quantum access to the decapsulation oracle. In our paper, we just consider in CC security for the sake of simplicity. Okay, so let me talk about our technicals in a high level. Here, due to the time limit, we only talk about the technical used to prove our new MRE way-to hiding lemma. The first step is to model a Q-ROM adversary with query times Q. In this talk, we only model a Q-ROM adversary A with query times 2 as an example to explain our technical. Here, A has input Z and quantum oracle set to O. It finally outputs a single bit B. We model A as a sequence of unitaries, where U2 and U1 are attack unitaries between oracle queries to O. Precise Z is an initial state related to the input Z. M is a final binary projective measurement used to compute B. So by the basic rules of quantum computation, we can write the probability that A outputs 1 under O equals G and O equals H as these two square norms, where we denote precise G as this state and precise H as this state. So next we can compute the advantage of A by applying the lemma 3.1 of this paper, and we know that the magnitude of this inner product is upper bound of the distinguishing advantage of A. So we note that this inner product has a term psi G minus psi H. So our next step is to decompose these states. Here we would like to mention that the MRM one-way-to hiding lemma proposed by Kuchta et al. Also decomposes these states, and they use the hybrid argument as follows. The minus GH and plus GH are added between psi G minus psi G. However, this hybrid argument will inevitably introduce a loss of query times Q. So we need to find a new way to decompose these states. Here Q equals 2 in our simple example. So in our paper, instead of using the hybrid argument, we decompose psi G minus psi H in an orthogonal way. We define a projected JM star as KTM star and BRM star on the Oracle input register. Then we decompose these states by JM star as follows. We first insert JM star plus I minus JM star after the G and H query, and they decompose this state and this state into following two parts by using the distributive law. Here I is the identity operator. For the first part, we keep it unchanged. For the second part, we decompose it again by inserting JM star plus I minus JM star after the other G and H query. And by the distributive law, we get this state. So we get these two formulas, and we can substitute this decomposed state into this inner product. In fact, thanks to our special orthogonal decomposition, and by using the Cauchy-Schwarz inequality and the basic property of inner product, we can transform this inner product into a product of two square roots, where the internal value is the sum of two special square norms. Okay, so our next step is to design two one-way adversaries and relate their success probabilities with these two sum of square norms. First, we construct adversary A1. It randomly chooses B from 0 and 1, prepares the state psi g minus h if B equals 0, and otherwise prepare the state psi g minus hh. Then it measures the oracle input register to get its final output x. So we note that A1 needs to prepare this state or this state, and this can be achieved by using the superposition oracle trick proposed by Binder et al. Under the condition that A1 has oracle access to both G and H. So by the basic rules of quantum computation, we know the success probability of A1 is exactly this sum of square norms under a constant factor 1/2. So we get this formula, and similarly we can construct an adversary A2 as follows. It first uses the superposition oracle trick to prepare the state M1 psi h plus psi g, and then performs HU2 dagger and this binary projective measurement J star I minus J star. Here U2 dagger denotes the inverse operation of U2. If this measurement success, that is A2 gets M star, it then directly stop and return M star. Otherwise, it proceeds to perform HU1 dagger and this measurement again to extract M star. If this second measurement still failed, A2 directly output bounds. So here this measurement can be performed by querying G and H, since G and H only differ on M star, and we can check whether X equals M star by querying G and H. So we can perform this measurement. At this point, we find that the success probability of A2 is exactly this sum of square norms. The intuition is that after we prepared this state and performed HU2 dagger, we get this state. For the next measurement, the probability we get M star is exactly this sum, this square norm. If this measurement failed, we get this state, and we proceed to perform HU1 dagger and this measurement again to extract M star. Now the probability we get M star in this second measurement is exactly this square norm. So during our computation, even if the extraction failed in the first measurement, we can still compute it and hope to succeed in later measurements. So we get this formula under A1 and A2 constructed above. We can let B be a new adversary that runs B A1 and A2 check whether their output equals M star by querying G and H. We can conclude that the success probability of B is greater than or equal to the success probability of A1 and A2. So we get this formula. Here we would like to stress that the adversary A2 constructed above had a structure that first measure, then perform U1 dagger and this measurement again to extract M star. So we call our new Y2 hiding lemma measure 1 extract Y2 hiding, or MRE Y2 hiding. Here the rewand correspond to U1 dagger and U2 dagger because performing these operations, we will revert collapse the state back to previous states, intuitively speaking. Okay, so here we only consider the anniversary with query times 2, but we can directly lift our about technical by induction to account for anniversary with arbitrary query times q. So we prove our new Y2 hiding lemma, and which has loose of the query times the square root of q. Okay, so now I give a summary. In our paper, we prove a new tighter Y2 hiding variant, MRE Y2 hiding, and then we give tighter in CC proofs of the FO-like transformation in the Q room by using our new Y2 hiding variant. Here we would like to stress that similar with the MRIM Y2 hiding lemma proposed by Kuchta et al., our MRE Y2 hiding lemma also bypass the impossible result given by Jiang et al. In fact, Jiang et al. Proved that the square root advantage loss of a Y2 hiding lemma is unavoidable in the black box manner. However, the adversary B in our MRE Y2 hiding lemma needs to perform the inverse of A's unitaries. So we actually use the invertibility of a unitary quantum root, and this does not belong to black box reduction. It is non-black box reduction or semi-black box reduction. So we bypass Jiang et al.'s impossible results and achieve bound without the square root advantage loss. Okay, so this is the end of my talk. Thank you for your attention. If you have any questions, please feel free to ask.
Okay, thank you a lot, Jinrong, for your great talk. Any questions from the audience? If not, I have firstly, can you elaborate a bit more? So it seems that the main reason why you were able to get this this tighter one-way to hiding is that you are basically introducing more queries. Like you initially started by this decomposition in which you are essentially kind of doubling the number of queries. Can you explain a bit the intuition of why this gives you this improvement?
So you mean what is the motivation of this work?
No. I mean, can you explain a bit where this improvement in the one-way to hiding comes from? Like what's the intuition?
Okay. So the intuition. Wait. So as we mentioned before, the MIM Y2 hiding lemma decompose these states by the hybrid argument. So but this hybrid argument will inevitably introduce a lot of query times q, because if you mix query times 2 and you use a hybrid argument, you will decompose this state into q parts. So when I consider this problem, I find psi g minus psi h is it has a very good algebra structure. So maybe we perform some orthogonal decomposition. We can get some useful information from their decomposition. For example, I made orthogonal decomposition. So we get James Stark here, and we can use you can use the basic property of inner product and some inequality to get this formula. So if you get this formula, you will see this is intuitively we can so you can construct an adversary to extract M star because there is exactly J M star. So maybe we can construct some one-way adversaries and make their success probability is exactly the sum of square norms. Yes.
Okay, thank you. Other questions? So maybe I have another question while you are here at this decomposition part. So is this also where the place where you make non-black box reduction, because you are saying in the end that there is like some step where you can avoid the impossibility result because you make like a non-black box reduction. Is it exactly in this decomposition that you are just showing?
Sorry, can you speak it again?
Yeah. I was just curious. So, like at the end, you were saying that you are avoiding this impossibility result. So you were able to get this tighter result because your reduction is a non-black box reduction. And I was just curious, like which step of your analysis is non-black box?
Okay. So here. So we decompose the distinguished advantage of A as the product of these two square roots. So for this square roots, we need to design a one-way adversary and relate their success probability with these two or this sum of two square norms. So here we have U2 dagger and U1 dagger. So if you want to construct adversary, you need to perform like here, you need to perform HU2 dagger and HU1 dagger. So this is not the black box reduction because you need to know the detailed quantum root of U2. You can perform the dagger of U2. So for example, if the algorithm A has quantum bits and classical bits, so you need to write this algorithm for quantum. You can know the detailed code of U2 and you can perform this U2 dagger. Otherwise, you cannot this A2 is cannot perform it.
I see. Okay. Thanks a lot, Changxia. Other final questions? Okay, so just one very high level. So do you think your framework can also be applied for like other security definitions? Like now that you have obtained this like tighter one way to hiding, can you also use it for like other applications or like to derive other tighter security analyses?
If you focus on the security of the Fujisaki-Okamoto transformation, maybe we can, for example, some special security of Fujisaki-Okamoto transformation, like anonymity or KDM. Maybe this one-to hiding lemma can be applied, but for some other transformations, maybe you cannot, because our one-to hiding lemma is it is non-adaptively reprogrammed. So like for Samir, maybe we need some adaptive reprogramming. At this time, we cannot our one-to hiding. Okay.
Okay, great. Thank you so much. So let's thank Zhangxia again for the great talk, and let's thank all the speakers of the session. And I guess the conference ends. So yeah, thank you everyone.